yesterday we defined the equation of the line, right? So we say that the line in the higher dimensions can be defined using the vectors, right? If we know the coordinates of one of the points on this line was the coordinates x0, y0, and z0, right? And a vector which is parallel. Okay, so let's draw the coordinate system. This is going to be a coordinate system, x, y, and z. And if we know the vector which is going to be parallel to this line, then we can build the equation of the line, right? We said, hey, if I would like to create an equation, it means that, so this is going to be one vector here, right? You see, so one vector is pointing here. And I would like to find the coordinates of this point P. It means that I can define this point using another vector as well, right? So let's say this is going to be R0 vector, and this is going to be R vector, okay? If you subtract the R0 from the R, what kind of, or R from minus R0, what kind of vector you will get? Do you remember the geometric operation with the vectors? Right? So if you subtract R or P minus P0, what kind of vector it gives you? Or R minus R0. So do you remember, so if you had the two vectors, which are going to start from the same point, right? This is going to be R and R0 and R. If you subtract them, geometrically, this is the connection of the ending points, right? So if it goes there, this is going to be, it always goes from negative to the positive. Do you remember? So if you put the two vectors, the subtraction of these two vectors, it is when we connect the ending points, and the direction of this vector goes from negative to the positive, right? If it goes in like this vector is going to be R minus R0 vector, right? Actually, on this line, I'm going to have this vector, sorry. So this vector here is equal to R minus R0. You understand this? So this is coming from the definition of the subtraction of the two vectors geometrically, right? So we've got one vector which is pointing on one point on the line, and we're defining another vector which is pointing out to the another point. And if we subtract them, these two vectors, we're going to have this vector, and obviously this vector is going to be parallel to our vector, which is given, right? And we've got a condition of the parallelity of the two vectors. It is R minus R0 is equal some constant multiplied to the u, right? So the two vectors are parallel if we can obtain the one of the vectors by multiplying a constant into the another one, right? So from here we can obtain the coordinates or the vector which is pointing out to the second point. It is going to be R is equal to the R0 plus TU, right? So this is the vector equation, right? Because you're putting, so this vector is given, this vector is given. R0 and U is given, right? R0 is one vector which is pointing out to our point on the plane, and U is given as the vector which is parallel to our line, right? And by putting different values for the input for our parameter, we can find all the vectors which are pointing out to all the points on this line, okay? Do you understand this definition of the vector equation, right? Previously, we used to have the line and a lot of points, and we can define the coordinates of the point with one equation. For example, y is equal to the chi x plus y, b, right? If you put some input instead of x, it is going to give you y, and you can build the one point by summing the x coordinate and the y coordinate of the point. So now, if you put different values for the parameter t, you're going to get a lot of vectors which are pointing to a lot of points on the line. Okay? So this is very interesting part of the calculus. This is called the analytic geometry. And the beauty of this analytic geometry is we can do a lot of things without imagination, kind of. Okay? So we can do a lot of things. I mean, if you like the calculus because of the calculations, it is the right place here. So you can do a lot of geometry without geometry. Kind of. Only with the vectors and calculations. Okay? And everything is like, everything which we're doing here is very intuitive and logical, right? So we've got the two vectors, we did something, and we're getting more and more rules. Okay, so now what I want, so this is the vector equation of the line, which is very simple, right? Okay, so now let's talk about the equation of the plane. So when we define the planes, it is really important for us to define the vector, which is going to be called as a normal vector. So this is going to be n. It's called n vector is the normal vector. And by the definition, the normal vector is perpendicular to the plane. Is perpendicular to the plane. What does it mean? It means that if I build some vector on a plane, any vector, this vector n is going to be perpendicular to any vector on this plane. Okay? So this n vector is perpendicular to the plane. It means that n is perpendicular to every single vector on the plane. Right? Because we know that we can move the vectors to any place, right? If you have one vector here, you can just put it here, and this is going to be perpendicular. Right? So this is really important notation. So we say that this normal vector is coming with the components. So let's say it's coming with the components A, B, and C. Okay? And at the same time, we know the coordinates of one of the points here. Okay? So we know one coordinate, P0, is going to have the coordinates x0, y0, z0. And so since recently we're defining the points with the vectors, right? So what kind of vector geometrically we can draw for this point? R0. What is our vector R0? It is coming from the origin and pointing to this point, right? Do you understand this? So it's coming from the bottom, right? So this is vector R0. Okay? So if we're given a plane, so in order to construct this, we need the coordinates of one point, or one vector, which is pointing to one of the points on this plane. And we need to know also the normal vector of this plane. Okay? Normal vector is a very important feature of the planes. It is a vector which is perpendicular to this plane or to any vector on this plane. Okay? So now what we want is, we would like to build the equation of the plane. What does it mean when we talk about the equation of the plane? It means that we would like to figure out some rule, right? So that it allows us to find all the points on this plane, right? Or it allows us to find all the vectors which are pointing into the points, onto the points on this plane. Okay? So for example, I would like to know, hey, I would like to choose any point here. This is going to be P with the coordinates x, y, and z. And I would like to know its coordinates. Okay? Or you can choose any other vector, any other point on the plane. Okay? In order to do this, what I'm going to do is, I would like to define this point P using another vector, with the R. So how the R should look like here? From the origin to this point, right? So we need to do the point, which is going from the origin to this point, R. Okay? So this is our vector R0, and this is vector R. So what is saying, is it possible to create a vector on the plane now with these t vectors? If you have the t vectors, which are starting from the origin, if you subtract them, you're going to have a vector, which is the connection of this t ending points, and this is going to be a vector on the plane, right? Do you understand this? So we can draw them separately. So this is going to be our vector R. This is vector R0, right? If you connect them, this is going to be their subtraction, right? Okay, let's connect them. And this vector is equal to what? So R0 minus R, right? Because it always goes from the negative to the positive. R0 to the R, okay? Or you can just change its direction so that we will have the common notation. It's going to be R minus R0. Do you understand this? Okay. So now, what kind of feature, what is the connection between this black vector and the red vector? So please note that normal vector is not, so you've got a plane, and you can put this normal vector to any place, right? Whenever you put this, it is going to be perpendicular to the plane, okay? So this is the feature of the normal vector, okay? So now, what is the connection between the normal vector and this vector? The dot product of this vector is equal, so the dot product of this black vector to this red vector is equal to the 0, right? Because the normal vector is perpendicular to the plane, it means that normal vector is perpendicular to every single vector on the plane. Right? Okay. So it means that the dot product to the R minus R0 multiplied to the n is equal to the 0. Okay, that's it. This is the equation of the plane.